we move on to the second part of this unit. Note down. Transient or unsteady state conduction. Transient or unsteady state conduction. So far our discussion has been limited to steady state. So where it is reflected in the mathematical equation for the general conduction equation on the right hand side. We take the general conduction equation in three-dimensional condition. Dou square d by dou x square plus dou square d by dou y square plus dou square d by dou z square plus q dot by k is equal to right 1 by alpha into dou d by dou t, right? Dou temperature by dou time. So there, with the assumption that the cases are under steady state condition, right hand side is made 0, and with other assumptions like this one dimension, we have neglected gradient in y and z directions. With other assumption that there are no internal heat generations, q dot, we solved some problem. But progressively we included q dot in some stage, right? And now we are including time also. And in the syllabus that we have in this subject, now we are not looking at two-dimensional heat transfer. And three-dimensional is even more difficult, right? Complex. You need to develop mathematical models for that. So the simplest case that we are considering as part of the syllabus that you have. So now, what does it mean, right? Why have you not considered the time factor so far, and why are we including it now? So practically, do you think steady state condition exists in any device that you see? It's very difficult. It's ideal condition. Only under what you say controlled environment you can make it possible. But all practical applications mostly will come under unsteady state condition. What's the difference between two? The properties that you consider, right, will vary with time. They will not remain constant with time. Suppose if you take temperature in this room, right, will it vary with time or doesn't vary? It varies. So it will be very hot in the afternoon, say at 2 o'clock, 3 o'clock, will be having lesser temperature early in the morning. So these, suppose if you record the temperatures of this room and draw a plot, time versus temperature. So this varies, and if it remains constant, then that is steady state condition. You can make it a steady state condition intentionally. Naturally it is not. Intentionally what can you do? You can fix an air conditioner here and set it at 25 degrees centigrade. Irrespective of the temperature outside, that will remain at 25. Now that's the external setting. That's not natural happening here in this room. So is the case in any practical application. If you take IC engines, heating or cooling, right? Heat is generated internally during one stroke when gases or fuels are burned inside, and then that heat is transferred to the surroundings or the water that is circulated around. So there is a continuous process of heating and cooling of engine cylinder wall or cylinder surface. So therefore, if you measure the temperature of the cylinder of the IC engine, it's continuously changing, right? So you can consider many such cases, right? The heat treatment of metals, process like annealing, benching, right? So during the heat treatment of metals, will the temperature remain constant with time? It will not. It will change. Suppose if you take other practical application that we all know, cooling or freezing of food, right? So food, the moment you take it out of your kitchen, its temperature drops down, and unless and until it comes in equilibrium with surroundings, the temperature keeps changing. Only when it comes in equilibrium with surroundings, then you can consider it as a steady state as far as its temperature is concerned. And there may be, variation in other properties like taste, flavor, its quality. It may not remain the same. The food which is today cannot be of the same quality tomorrow if you eat alone, right? It perishes. So similarly, the same food open the door of a refrigerator and keep it inside, and again temperature varies. So these are all the applications, practical applications, where unsteady state condition prevails, right? So now, here what are the parameters that influence this? The surface level. Whenever we talk of a solid body, it is kept in some surroundings or some ambience, some place where it is surrounded by a fluid. It could be water or it could be air. So any machine element you take that is kept somewhere. What is it surrounded by? Surrounded by the atmosphere, or if it is a controlled environment. Suppose if you keep it in refrigerator, let's say, again there is ambience to it. So the object or element, machine element that we are considering, right, is placed in surroundings which is at its own temperature and has its own convection coefficient. So therefore now the that system depends on the heat transfer between the solid surface and the surrounding fluid with which it is in contact. So those conditions, those convection conditions at the surface are one of the important influencing factors. And then it could be radiation also. Radiation effect will also be there. You see you are somewhere and you can still feel the radiation of the sun, right? Being so far away from it. Surface temperature or heat flux. What is the temperature of the surface and what is the heat flux of the surface? And what is the heat generated internally? So all these will influence this transient conduction. And now how do you solve these problems, right? So obviously we cannot use any of the equations that we derived earlier, because now the right hand side dou T by dou T is coming into effect. Now if you have to solve that equation, you have to consider it. Right? Suppose one dimensional unsteady state condition, you have to take dou square T by dou x square is equal 1 by alpha into dou T by dou T, and you have to solve that equation. Now we can simplify some of the cases of transient conduction with some assumptions. Right? So now we will start our simplified assumption of this. Let's say there is a solid body like this of arbitrary shape, which is initially at a temperature of Ti. I stands for initial condition. It is said T less than 0. What is the meaning of T less than 0? Can time be less than 0? Can time be less than 0? But meaning is, suppose if you are supposed to come to the attendant, not to write an exam, let's say reporting time is 9. You come at 8:55, let's say. What do you say? You are late by 5 minutes. So you are at -5. Isn't absolute time is 8:55, but you are denied the opportunity to enter the hall because you are at -5. So now the reference point is that. So when I say less than 0, that means before you start analyzing it, before you start experimenting on it, before the action commences, that we are calling it as T less than 0, right? And at that point T is equal to Ti, that is the initial temperature. Now it is dropped into the liquid, which is at its own temperature, T infinity, and if the T infinity is less than Ti, that means this object will be cooled, will be subject to loss of heat from it. Now when it is losing the heat, what is that it is, what is happening inside? It loses its internal energy. See, imagine something like this. What is this losing of internal energy or gaining of internal energy? You have, say, 10,000 rupees in your bank balance, right? In your bank, it's deposited. Right? Today you have withdrawn, say, 100 rupees, right? So that withdrawing heat, 1,000 rupees is like losing heat to the surroundings. It is losing heat. And what is the effect of that? What is the effect of you withdrawing 1,000? Your bank balance changed. So what happened to your bank balance? It is reduced. That is like internal energy. Your bank is energy. Whatever is there can be combined with the energy. Now its energy is reduced. Its value is reduced. Here the value, index of value is energy in this problem. Their index of value is currency. Otherwise there is no difference. So whatever is taken out is resulting in reduction of its value. Right? This is what we put it in the form of first law of thermodynamics. Heat transfer is equal to dq is equal to du plus dw. Right? If dw is 0, which is the case for this solid body, doesn't have any change in volume. Right? So work transfer is 0. So therefore heat transfer dq is equal to change in internal energy dq. So therefore thermodynamic law is like law of nature. It's not something which you don't know or which you haven't experienced. It's same, but it is just given a shape to it, a meaning to it. Now we will proceed with one case by other case, one case after the other case. And before we take those cases, you need to have the knowledge of certain dimensionless parameters that are useful in this analysis. One of them is Biot number. It is a dimensionless parameter which is given mathematically as HLC by K, where H is heat transfer coefficient, LC here is characteristic length. Right? See the meaning of the letters that we take changes, right? It's not constant. You cannot just link this to the LC that you used earlier in fins. There it is corrected length. Actual length is slightly increased to compensate or to include the area that is not covered in the integration. Here this LC is characteristic length. Right? And its definition is ratio of volume to the surface area. Right? And K is the thermal conductivity of the solid. Now, this being the case, the Biot number can be little understood better. Right? Like, see, Biot number is HLC by K. Now, what we can do, let's say I am multiplying and dividing it with Ks. Right? Now I can write this as LC by K into HAS. Can I write it like this? Right. This is equal to LC by K, ARAS. S refers to surface area, that's it. Divided by 1 by HAS. Can I write like this? Is it possible? Now, this is the Biot number. And what is L by K? L by K is conductive resistance. Right? In the Fourier's law, we have to do this. And what is 1 by HA? This is convective resistance. So now, the physical significance of Biot number is this. It is a relative measure of the conductive resistance to the convective resistance. You can further represent it in the form of temperature drop as well. See, suppose Q is equal to, right? This is in series. Suppose there is heat transfer between the solid and then solid to surrounding fluid. Now the heat transfer is series. So you can write this as, right, heat transfer by the temperature difference within the solid, divided by resistance offered by the solid. So this is LC by LC by K, I can write this as conductive resistance. Right? Is equal to the same heat transfer again is to be dissipated to the surroundings by convection. Now in the convection, what is the temperature difference that you get? Delta T between solid and the fluid. Right? Ts minus T infinity. Ts is solid temperature, T infinity is surrounding fluid. Divided by what? Convective resistance. Right? So this is like Q is equal to HA delta T, where delta T is temperature of solid. surrounding fluid. Right? So this is temperature between 2 points within the solid. Right? T1 minus T2 from one point to another point in the same medium. Here this is from one medium to another. Now by comparing these two, what do you get? Suppose if you get this conduction, take this to right side. R conduction by R convection is equal to delta T solid divided by delta T between solid and fluid. So therefore, what does it mean? This is also a measure of relative drop in temperature. This is the drop in the temperature within the solid, and this is the drop in the temperature between the solid. So Biot number will also measure the relativity of drop in temperature. But it's a natural consequence of this. Okay. So please make a note of this. This is an important point that you need to understand. There is another dimensionless parameter that we use in this analysis known as Fourier number. Fourier number written as F4 is equal to alpha into T by LC square. It is called dimensionless time. There is a time here, but the product of all this is of course dimensionless, and the general name that is given to it is dimensionless time. So these two dimensionless numbers are useful in the analysis that we are going to make now. Now, I will complete this. Characteristic length, as I said earlier, is defined as a ratio of volume of a given solid to its surface area. Now let's take three different cases. A plane wall of certain thickness, say L, and area on either side A. So for this case, volume V is A into L, right? Divided by surface area. A on one side and A on the other side. So A plus A is 2A. So this becomes L by 2, right? And similarly, for cylinder and sphere also we can do. Volume is pi r square L. Surface area is 2 pi r. R being the radius of the cylinder. So then this is R by 2. For sphere it is, volume is 4 by 3 pi r cube. And area is 4 pi r square. So this is R by 3. L by 2, R by 2 and R by 3. We will take this case. This is an important case in this chapter as far as your examinations are concerned. Systems with negligible internal resistance, which are called lumped masses. Please make a note. Systems with, again take the same case, a solid body kept in a surrounding fluid that is at different temperature. Now depending on whether it is hotter or cooler compared to this, it will lose or gain the temperature, right? Or whether receive the heat or lose the heat. Now in this case, it will lose the heat. Okay. So now, if you explode it, zoom it out, this is like this. It is an arbitrarily shaped body which is having a volume V, specific heat C and density rho. Initially this is at temperature Ti, right, when T is less than 0. And this is losing heat the surrounding fluid, which is at T infinity, where T infinity is less than Ti. Now, for this case, please try to observe it carefully. For the heat to transfer from this body to the surroundings, it has to travel through two media. One is solid itself, another is to the surroundings, from the solid surface to the surroundings. So for the heat to transfer within the solid, it has to overcome or it has to encounter the conductive resistance, which we call it as internal resistance. Within the system is internal, right? So that is the resistance that opposes the heat transfer within the body. And what is the resistance that opposes the heat transfer from the surface to the surroundings? That is convective resistance, which we also call it as surface resistance. External resistance or surface resistance or convective resistance. Please make a note, all are the same. When I say convective resistance, I can also consider it as surface resistance because the resistance is offered at the surface. Or I can also call it as external resistance. When I say the resistance within the body, I can call it as conductive resistance or internal resistance. Now, we are taking a case where the internal resistance is negligible. What does it mean? The internal resistance is conductive resistance, which is equal to L by Ka, right? The internal resistance, internal, is nothing but conductive resistance, which is equal to L or Lc by A is the surface. See, for a given body, length is fixed, area is fixed. Now, what is the variable here that influences the resistance? Thermal conductivity. So, for bodies whose thermal conductivities are closer to infinity, are very huge, then this whole value will be very minimum, and when it is infinity, it will become 0. That means this analysis is an approximation for materials which have larger thermal conductivities, like metal, silver, aluminium, right, copper, diamond. For such objects, thermal conductivity is very high, and because that is sitting in the denominator, the whole value will become very less. So therefore, this is applicable when this resistance is less. When is this resistance less? When K is very high. When K is very high, this whole resistance is very less or negligible. So, for larger values of K, right, as K tends to say infinity, this internal resistance, internal or conductive resistance, tends to be 0. So, suppose if internal resistance is closer to 0, if not 0, then what will be the Biot number value? Meaning of this is what? Biot number will it be less or more? Is very, very less, in fact. So if it is less than, say, up to 0.1, if you want to put it, if it is less than 0.1, this approximation is good. It need not be 0, right? It should be small. I said it is not possible to have infinite value of K. Therefore, obviously, it is not possible to have 0. It's the closest approximation. Therefore, you need not have 0 Biot value. It can be closer to that. So, when Biot number is less than 0.1 instant of time at a temperature of T, right, at a given instant of time, unknown temperature. Initially, it is at Ti, but once it is dumped into this fluid, right, its temperature changes because of the heat transfer between this body and surrounding fluid. So after some time T can be any value between 0 and maximum time. At that particular instant of time, if you consider energy balance or first law of thermodynamics, see the heat transfer here is from the object or solid body